This is the EdExcel AS Level Further Maths Paper 1, covering the Core Pure content, and it's from the 2021 series. Question number 1. We are given the matrix P, 0, 1, minus 1, 0. We are given the matrix Q, 1, 0, 0, 3. For part A, for the first part, we have to describe fully the single geometric transformation P represented by the matrix P. Well, we've got here 0, 1, minus 1, and 0. We begin with 1, 0, and 0, 1. What we end up with is 0, 1 and minus 1, 0. So this line here ends up here at the point 0, 1, and the 0, 1 here ends up at minus 1, 0. So what's happened here? Well, here we have rotated, and here we have also rotated. What can we conclude then? We have rotated 90 degrees anti-clockwise about the origin. And then for the next part, we have to describe fully the single geometrical transformation Q represented by the matrix Q. Similar to what we did in the first part of part A, we begin with 1, 0 and 0, 1. What's happening is the 1, 0 here remains where it is, and the 0, 1 ends up at 0, 3. So we move over here to 0, 3. You can see then we've stretched this point 0, 1 to the point 0, 3 only in the y direction. And so we have a stretch scale factor 3 parallel to the y-axis. Now, the transformation P followed by the transformation Q is the transformation R, which is represented by the matrix R. We have to determine R. So, for part B, R is equal to Q multiplied by P. We have P followed by Q, which is equal to R, which is why we work it out in this order. We work backwards. So, if we find out what R is, we've got the matrix Q, which is 1, 0, 0, 3. Multiplied by P, which is 0, 1, minus 1, 0. So we have 0, 1, minus 1, and 0. And if we work all of this out, we can use our matrix feature on our calculator to help us work this out. Let's define the matrix A to be 1, 0, 0, 3. Let's define the matrix B to equal 0, minus 1, 1, 0. And then we will do matrix A times matrix B. What we end up with is 0 minus 1, 3, and 0. Here is the matrix R. And now, for part C, for the first part, we have to evaluate the determinant of R. The determinant of the matrix R, that's equal to the following. We've got 0, minus 1, 3, 0. These entries are enclosed in straight lined brackets. So if we work this out, we have 0 times by 0 minus 1 times by 3. So we have minus 1 times 3, which is positive 3. And now for the next part of part C, we have to explain how the value obtained in Ci relates to the transformation R. What we have worked out here is the area scale formatter of the transformation. Question number 2. The cubic equation 9x cubed minus 5x squared plus 4x plus 7 equals 0 has roots alpha, beta and gamma. Without solving the equation, we have to find the cubic equation whose roots are 3 alpha minus 2, 3 beta minus 2 and 3 gamma minus 2, giving an answer in the form aw cubed plus bw squared plus cw plus d, where a, b, c and d are integers to be determined. The first thing we will do, we will let w equal 3x minus 2. Each of these roots are of this form here. And if we rearrange for x, of course x is equal to w plus 2 over 3. What we will do now is replace the x with w plus 2 over 3. And if we do that, we have 9x cubed, so we have 9 multiplied by w plus 2 over 3 cubed minus 5x squared. So we subtract 5 lots of w plus 2 over 3 squared plus 4x. So we add on 4 lots of w plus 2 over 3. We then add on 7. The result of all this is 0. Now, if we simplify, we have 9 multiplied by 1 over 3 cubed. So we have 1 over 3 multiplied by w plus 2 cubed. So that will be w plus 2 cubed divided by 3, and then minus 5 over 3 squared, that's minus 5 over 9. So we then subtract off 5 lots of w plus 2 squared over 9, and then we add on 4 lots of w plus 2 over 3. We then add on 7. The result of this is all equal to 0. Now w plus 2 all cubed using the binomial expansion, that's equal to w cubed plus 6w squared plus 12w plus 8, and then we divide this by 3, and then we've got minus 5 lots of w plus 2 all squared, so that's w squared plus 4w plus 4, and then we divide this by 9, and then we add on 4 lots of w plus 2 over 3, and then we add on 7. The result of all this is equal to 0. So let's simplify as much as we can. We have here w cubed over 3 then we have 6w squared over 3, so that's 2w squared. 12w over 3 is 4w. 8 over 3 is what's being added to this. And then we have minus 5 times w squared over 9. So that's minus 5 w squared over 9. Minus 5 times by 4w divided by 9. That's minus 20 w over 9. Minus 5 times by 4 is minus 20. And then we're dividing this by 9. And then we have 4w over 3. And then we have 8 over 3. And then we add on 7. It's all equal to 0. And if we simplify as much as we can, we have w cubed over 3. And then we have 2w squared minus 5 over 9w squared. So that will be 13 over 9w squared. So we add on 13w squared over 9. And then we have 4w minus 20w over 9 plus 4w over 3. So that's 28w over 9. And then 8 over 3 minus 20 over 9 plus 8 over 3 plus 7. That will be 91 over 9. All of this is equal to 0. And if we multiply through by 9, we can then conclude that 3w cubed plus 13w squared plus 28w plus 91 equals 0. This is the cubic equation which has roots 3 alpha minus 2, 3 beta minus 2, and 3 gamma minus 2. Question number 3. For part A, we have to use the standard results for summations to show that for all positive integers n, the sum from r equals 1 to r equals n of 5r minus 2 all squared is equal to 1/6 n lots of a n squared plus b n plus c, where a, b and c are integers to be determined. Well, for part A, let's begin by finding out what 5r minus 2 all squared is. If we work out what this is the same as 25r squared minus 20r plus 4. So what we will be doing is finding out the sum from r equals 1 to r equals n of 25r squared minus 20r plus 4. And we can split this summation up as follows. First of all, we can split it up as 25 lots of the sum from r equals 1 to r equals n of r squared minus 20 lots of the sum from r equals 1 to r equals n of r, and then we add on 4 lots of the sum from r equals 1 to r equals n of 1. Now in the formula book here, we have highlighted what the result of the sum from r equals 1 to r equals n of r squared is. That's 1/6 n lots of n plus 1 lots of 2n plus 1. So using that result, we can simplify even further. We have 25 multiplied by 1/6 n lots of n plus 1 lots of 2n plus 1 and then we have minus 20 lots of 1/2 n lots of n plus 1, and then we add on 4n. Now we need to simplify all of this. If we were to simplify all of this, we have 25 times by a sixth, which is 25 over 6, and then we multiply this by n, and then n plus 1, and then 2n plus 1, and then we have minus 20 times by a half, that's minus 10. So we've got minus 10n lots of n plus 1, and then we add on 4n. Now if we pay attention to the question has a 1/6 n factored outside of this bracket. So we will also factorize out a 1/6 n. Each term contains an n, and if we factorize out the 1/6, inside this bracket we've got 25 lots of n plus 1 lots of 2n plus 1. Of course, this multiplied by 6n gives this result here, and then a 6th n times by something gives 10n. Well, that will be 60. Of course, multiplying minus 60 by the 1/6 n gives minus 10n, and then we still have the n plus 1. And then a 6th n times by something gives 4n. Well, that will just be 24. So if we simplify this bigger bracket as much as we can, well, on the outside remaining we still have this 1/6 n, and then we have 25 multiplied by, well, n times by 2n is 2n squared. N times by 1 plus 2n times 1, that's 3n. And then we have 1 times by 1, which is 1. And then we subtract 60n, subtract another 60, and then add 24. So now let's try to simplify this even further. If we expand the 25 into this bracket, well, remaining on the outside, we still have the 1/6 n. And then 25 times by 2n squared, that's 50 n squared. 25 times by 3n, that's 75 n. 25 times 1, that's 25. And then we have minus 60 n. Minus 60, and then we add on 24. And if we try to simplify this even further, we have 1/6 n. 50 n squared is the only n squared term. 75n minus 60n, that's 15n. 25 minus 60, and then adding on 24, that's minus 11. Hence we've simplified this result here. And now for part B, hence determine the value of k for which the sum from r equals 1 to r equals k of 50r minus 2 all squared is equal to 94k squared. And if we use the result which we found in part A, we'll replace the n with k. So, for part B, we begin by writing out the summation from r equals 1 to r equals k of 5r minus 2 squared. This is equal to 94k squared. And if we use this result, replacing the n with k, we have 1/6 k lots of 50k squared plus 15k minus 11 equals 94k squared. If we multiply through by 6 and then expand the k into the bracket, we have k times by 50k squared, that's 50k cubed. And then we have k times by 15k, that's 15k squared. K times by minus 11, that's minus 11k. And this is equal to 6 times by 94k squared, which is 564k squared. So let's simplify this even further. If we take everything over to one side, we have 50k cubed, and then 15k squared minus 564k squared, that's minus 549k squared. And then we've got the minus 11k. This is all equal to 0. And if I factorize out a k, we've got k lots of 50k squared minus 549k minus 11. This is all equal to 0. So if we factorize, we've got k lots of k minus 11 lots of 50k plus 1. This is all equal to 0, and if we solve this, we've got k equals 0. If k minus 11 is 0, that means k is 11, and if 50k plus 1 is 0, that means k is equal to minus 1 over 50. And so what we can conclude then is k equals 11 is the only solution. Question number 4. We've got the matrix M, which is equal to 2, 1, 4, k2 minus 2, 4, 1 minus 2, and the matrix N. That's equal to k minus 7, 6, minus 10, 2, minus 20, 24, minus 3, 2, and minus 1. K is a constant, and for part A we have to determine in simplest form, in terms of K, the matrix Mn. So for part A, the matrix Mn, we've got the matrix M, 2, k, 4, 1, 2, 1, 4, minus 2, and minus 2. We will multiply this by k minus 7, 6, minus 10, 2, minus 20, 24, minus 3, 2, minus 1. So let's work all of this out. We begin by moving across here and then down here. And if we do that, we have 2 times by k minus 7, 1 lots of 2, and then 4 lots of minus 3. And then we will be moving down here for the next element, and then across here. So we've got 2 lots of 6 plus 1 lots of minus 20 plus 4 lots of 2, and then we move down here. So we've got 2 lots of minus 10, and then we've got 1 lots of 24, and then we've got 4 lots of minus 1. So now we need to move across here and then down here. We've got k lots of k minus 7, and then we've got 2 lots of 2, And then we've got minus 2, lots of minus 3. And then we go down here. So we've got k, lots of 6, plus 2, lots of minus 20, minus 2, lots of 2, and then we move down here. So we've got k, lots of minus 10, plus 2, lots of 24, and then we've got minus 2, lots of minus 1. And then we go across here, and then we go down here. So we've got 4, lots of k minus 7, plus 1, lots of 2, and then we've got minus 2, lots of minus 3, and then if we move the arrow, so we're going down here now, we've got 4, lots of 6, 1, lots of minus 20, and then we've got 2, lots of 2, and then if we go down here, we've got 4, lots of minus 10, 1, lots of 24, and then we've got minus 2, lots of minus 1. So this is what we need to simplify. So if we simplify all this, we've got 2k, and then we've got minus 14 plus 1 minus 12. So that simplifies to 2k minus 24. And then here we've got k times by k, which is k squared. And then we've got minus 7k. And then we've got 4 plus 6, which is 10. So that's this element complete. And then here we've got 4 times by k. And then we've got minus 28 plus 1 plus 6, so that's minus 20. And then here we've got 12 minus 20 plus 4, that's 0. Here we've got 6k minus 20 times 2, which is minus 40, minus another 4, that's minus 44. And then here we've got 24 minus 20 plus 4, which is 0. And then here we've got minus 20 plus 24 minus 4, which is 0. Here we've got minus 10k. And then here we've got 48 plus 2, which is 50. And then here we've got minus 40 plus 24 plus 2, which is minus 14. And so what we can see here then is we have the matrix Mn, which is equal to the result we see here. And now for part B, given that k is equal to 5, we have to write down Mn. So, for part B, with k equaling 5, for the first part, the matrix Mn, if we replace k with 5, here we've got 10 minus 24, which is minus 14. Then we've got 0 here and 0 here. And then here we've got 25 minus 35 plus 10, which is 0. Here we've got 60 minus 44. Rather, here we've got 30 minus 44, which is minus 14. And then here we've got minus 50 plus 50, which is 0. And here we've got 20 minus 20, which is 0. 0 here. And minus 14 here. So this is the matrix Mn. And now to find the inverse of the matrix M, for the next part, the inverse of the matrix M, well, knowing that k is equal to 5, if we go to the matrix menu, we've got 3 rows and 3 columns. We've got 2, 1, 4. K, we were told, is 5. Then we've got 2 minus 2, 4, 1 minus 2. And then press options. We load up matrix A. We want to take the inverse of this. So the inverse of this matrix, if we take out a minus 1 over 14, then here we've got minus 2, here we've got 6, and here we've got minus 10. Here we've got 2, here we've got minus 20, and here we've got here we've got positive 24, and then here we've got minus 3, here we've got 2, and then here we've got minus 1. So that's the inverse of the matrix M. Now, for part C, we have to solve the simultaneous equations 2x plus y plus 4z equals 2, 5x plus 2y minus 2z equals 3, and 4x plus y minus 2z equals minus 1. Here we have our system of equations, which we can write in matrix form. And if we were to write this system of equations in matrix form, we've got 2, 5, 4, 1, 2, 1, 4, minus 2, minus 2. This is multiplied by x, y, z, and the result of this is 2, 3, minus 1. Now, if we pay attention to what we have here, of course this result here is what the matrix M is. However, we've replaced K with 5. So when we come to find out what X, Y, Z is, then we need to take the inverse of M of both sides. And so if we do that, we've got 2, 5, 4, 1, 2, 1, 4, minus 2, minus 2, inversed, multiplied by 2, 5, 4, 1, 2, 2, 4, minus 2, minus 2, multiplied by X, Y, Z. And this is of course equal to the inverse, 2, 5, 4, 1, 2, 1, 4, minus 2, minus 2, inversed, multiplied by this vector, 2, 3, minus 1. And recognizing that the inverse multiplied by this matrix is just the identity matrix, so we have X, Y, Z. Now this inverse we worked out over here. So just copy and paste this. We worked out that result before. And then we're going to multiply this by 2, 3, minus 1. So if we work out what X, Y, Z is, press AC, options, matrix answer. Well, before we do that, let's define the matrix B with 3 rows, 1 column, 2, 3, minus 1. So then we've got matrix answer multiplied by matrix B. So we get the vector X, Y, Z equaling minus 12 over 7, 40 over 7, minus 1 over 14. And so, as coordinates, we have minus 12 over 7, 40 over 7, minus 1 over 14. And now for part D, we have to interpret the answer to part C geometrically. Of course, we have the coordinate of the only point at which the plane is represented by the equations in part C. Question number 5. We have figure 1 over here which shows an argon diagram. The set P of points that lie within the shaded region including its boundaries is defined by P equals, well, Z belongs to a set of complex numbers, where A is less than or equal to the mod of Z plus B plus Ci, which is less than or equal to D. A, B, C and D are integers. For part A, we have to write down the values of A, B, C and D. Well, what you'd hopefully find is the radius of the smaller circle is 1, and the radius of the larger circle is 2. And so, with that information, we can see that A and D are 1 and 2 respectively. Now, if we rewrite P as follows, we can rewrite P as Z belongs to a set of complex numbers. A is less than or equal to the mod of Z minus B minus C I, which is less than or equal to D. And from this, you should hopefully be able to spot what the center is. The center will be given by B, C. Of course, if we expand this out, we do indeed get the result Z plus B plus Ci. The minus and the minus give the positive. And so what can we also spot? Well, if the center is at minus 2, 1, that means B is equal to 2 and C is equal to minus 1. So let's just write down the values of A, B, C and D. By inspection, A is equal to 1, B is equal to 2, C is equal to minus 1, and D is equal to 2. Of course, we've got the center being at minus 2, 1, hence B is 2 and C is minus 1. The signs have changed. Now, for part B, the set Q is defined by Q equals, well, we've got Z belonging to a set of complex numbers. A is less than or equal to the mod of Z plus B plus Ci, which is less than or equal to D, and Z belongs to a set of complex numbers. The mod of Z minus I is less than or equal to the mod of Z minus 3i. We have to determine the exact area of the region defined by Q, giving your answer in its simplest form. Well, let us suppose for part B, we had Z minus I equaling the mod of Z minus 3i. If we were to rewrite this result, we can rewrite it as Z minus 0 plus I equaling the mod of Z minus 0 plus 3i. What we are after here is the perpendicular bisector. The perpendicular bisector, that would be y equals 2. And y equals 2, we can show over here. Here is the line y equals 2. And so where the mod of Z minus I is less than or equal to Z minus 3i, that will be below this line. And if we want it to satisfy the other region too, the region we need to work out is this region here. So Q is what we see shaded over here. So how can we go about this question? Well, we can find out the area enclosed between the two circles, but then we need to take away the bit above it that's in grey. How could we do that? Well, if we were to draw a triangle, what we'll do to begin with, before we draw a triangle, is draw a sector. If we have a sector over here, then we can find out the area of this sector and then subtract the area of this triangle that's over here. And that will tell us this grey portion here, and then we times it by 2 because we've got the same over here as well. So if we were to create a triangle, we have an angle theta over here, say, and the radius here is 2, the radius here is 1, and if we use simple trigonometry, the area of this triangle can be determined. Now, by Pythagoras, this length here is root 3. 2 squared take away 1 squared all square rooted is root 3. So let's begin by finding the angle theta. The angle theta, according to that triangle, is equal to the inverse cosine of 1 over 2, and this is equal to pi over 3. So now that we know this angle to be pi over 3, we can find the area of the triangle and the sector. So the area of the triangle, that's given by 1/2 times by the base, which is root 3, times by the height, which is 1. So the area of the triangle is root 3 over 2. This is the area of this shaded triangle. We can also find the area of the sector. We know the angle is pi over 3, and so the area of a sector, that's given by 1/2 times by radius squared, so that's times 2 squared, multiplied by pi over 3, and it turns out the area of the sector then, let's move this down here, the area of the sector then is 2 pi over 3. So what can we now do? Well, we can find out the shaded region, but before we do that, let's find out the area between the circles. The area in between the circles, we've got pi times by 2 squared, take away pi times by 1 squared, which is equal to 3 pi. So that's the area in between the circles. What we can now find out is the area above the circles, which is in grey. So what we can do now is find out this shaded area. So this shaded area is equal to 2. Now let's explain where this 2 comes from. We've got this part and this part over here. So this line is separating this shaded region and this shaded region. And that's through the symmetry of the circles. So that's where that 2 comes from. And then we take away Well, we've got we've got the area of the sector take away the area of the triangle. So the area of the sector, we know that's 2 pi over 3. We then take away the area of the sector, root 3 over 2. So if we work this out, the shaded area is 4 pi over 3 minus root 3. We've got the area in between the circles being 3 pi. So therefore, we can conclude that the required area will be the entire circle take away this grey bit over here. So the required area, which is what's highlighted, that's equal to 3 pi, which is the area in between the circles, and then we subtract the shaded area, 4 pi over 3 minus root 3. So therefore the required area is equal to, well, 3 pi minus 4 pi over 3. That's 5 pi over 3. And then the minus and the minus give a plus. So we add on root 3. The units are just units squared. So here we have found the required area, as we see here. Question number 6. A mining company has identified a mineral layer below ground. The mining company wishes to drill down to reach the mineral layer and models the situation as follows. With respect to a fixed origin O, the ground is modelled as a horizontal plane with Z equaling 0. The mineral layer is modelled as part of the plane containing the points A with coordinates 10, 5, minus 50, B with coordinates 15, 30, minus 45, and C with coordinates minus 5, 20, minus 60, where the units are in meters. For part A, we have to determine an equation for the plane containing A, B, and C, giving our answer in the form r dot n equals d. For part A, here is a sketch of our plane with the points A, B, and C on it. Now, we can find out what the equation of the plane is, first of all by defining what the vector AB is and what the vector AC is. And once we've done that, what we can also do is find out a normal vector. The normal vector is the vector over here. We'll call this normal vector n. And AB and AC are perpendicular to n, as we see in this diagram. So what we'll do to begin with is define the vector AB, and we'll also define the vector AC. So if we were to find out what AB is, the vector AB is equal to OB minus OA. So if we work this out, we have 15i plus 30j minus 45k minus 10i plus 5j minus 50k. And so therefore we can conclude the vector AB is equal to 5i plus 25j plus 5k. And if we find out what the vector AC is, the vector AC is equal to OC minus OA. So we have OC equaling minus 5i plus 20j minus 60k minus 10i plus 5j minus 50k. So AC is equal to minus 15i plus 15j minus 10k. We have found AB, we have also found AC. And with this information, what we can now do is find out the normal vector. So we will let the normal vector n be of the form AI plus BJ plus CK. We need to find out what A, B and C are. Now if that's the case, AB dot with n is equal to 0 and AC dot with n is equal to 0. The reason for that is the vectors AB and AC are perpendicular to n. So we have AB dot with n, this is equal to 0, and we also have AC dot with n equals 0, but let's just deal with this for now. We have AB, which is 5i plus 25j plus 5k. We will dot this with AI plus BJ plus CK. The result of this is equal to 0. So we have 5a plus 25b plus 5c equals 0, from which we can conclude A plus 5b plus c is equal to 0. We'll call this equation 1. What we also have is AC dot with n. This is equal to 0. So we have minus 15i plus 15j minus 10k dot with AI plus BJ plus CK. The result of this is equal to 0. So we have minus 15a plus 15b minus 10c equals 0, and therefore minus 3a plus 3b minus 2c is equal to 0. Call this equation 2. And now if we solve 1 and 2 simultaneously, well, for us to do that, we need a value of c. Now, there's no reason why I've chosen c. We could have chosen a or b to have a certain value, but what I will do is choose the value of c. What I will do is let c equal 1, and if I do that, we have equation 1 being a plus 5b plus 1 equaling 0, from which we can see a plus 5b equals minus 1. We'll call this 3. And we also have minus 3a plus 3b minus 2 lots of 1 equals 0, from which we can conclude minus 3a plus 3b is equal to 2. We'll call this equation 4. And now, if we solve equation 3 and equation 4 simultaneously, let's just for a moment use our calculator. We have 1a, 5b equaling minus 1, minus 3a plus 3b equals 2. So we have a value of a of minus 13 over 18, a value of b of minus 1 over 18, and of course we know c is equal to 1. So knowing the values of a, b and c, we can therefore conclude that the normal vector is equal to minus 13 over 18i minus 1 over 18j plus k. What we now need to do is find out what the value of the constant d is, and we can do that by recognizing that a, the point a dotted with n, gives that value. So given this point a and this normal vector, and if we go to the formula book, this is how d is defined. It's equal to minus a dot n, where a is a point with this position vector. So using d equals minus a dot with n, we can define d to equal minus, well, we've got a, which is 10i plus 5j minus 50k, and then we dot this with n, which is minus 13 over 18i minus 1 over 18j plus k. So if we find out what d is, well, we've got 10 times by minus 13 over 18 plus 5 times by minus 1 over 18 plus minus 50 times 1. So we end up with a value of minus 115 over 2. So we've got minus 115 over 2. So therefore d is equal to 115 over 2. And knowing what this normal vector is, we have r dot with n. Now n here is minus 13 over 18i minus 1 over 18j plus k. Well, if I expand this out, I also have the plus d all of this is equal to 0. Of course, r we can replace with x, y, z. That's just adapting this formula here. And so therefore, if I multiply through by 18, so if I times this by 18, and then take the negative of that, because I'm taking this over to the right hand side, we can therefore conclude that the equation of the plane, we have r dot with minus 13i minus j plus 18k is equal to minus 1035. This is the equation of the plane. We will call this equation of the plane pi. Call it pi 1 actually. This over here is the equation of the plane. For part B, we have to determine, according to the model, the acute angle between the ground and the plane containing the mineral layer. Give your answer to the nearest degree. Well, what do we know so far? We know so far the ground is modelled as a horizontal plane with equation z equals 0. What is that equation in vector form? Well, for part B, that equation in vector form is r dot with 0i plus 0j plus k equals 0. And if you want to convince yourself why that's the case, if I replace r with x, y, z, we have xi plus yj plus zk, and then this bit's the same. What you'd find if we work this out, we get z equals 0, which is why this is the equation of the plane with equation z equals 0. So, if I call this equation here pi 2, if I call this equation 1, and this, rather, if I call this equation 5, and if I call this equation 6, so requiring the angle between 5 and 6, well, what we'd have to do here is use the normals. Now, to find out the acute angle, we've got the cosine of alpha equaling the mod of n1 dot with n2 divided by the mod of n1 times the mod of n2. This is how we work out the acute angle. So if we use that, cos alpha, that's equal to, well, we know what the two normals are. That's minus 13i minus j plus 18k, and 0i plus 0j plus k. So, if we write everything down, we have minus 13i minus j plus 18k dot with 0i plus 0j plus k, and then we will divide this by, well, here we'd have minus 13 squared plus minus 1 squared plus 18 squared, and then here we'd have 0 squared plus 0 squared plus 1 squared, and then all of this will be square rooted. And then we take the modulus of that. So working this out, we have the absolute value of minus 13 times 0, which is 0, minus 1 times by 0, which is 0, and then we have 18 times 1, and on the bottom we've got square root of 13 squared plus 1 squared plus 18 squared multiplied by, well, here we've just got the square root of 1 squared. So we end up with 0.809, etc. So the inverse cosine of this, we get alpha equaling 35.9, etc. From which we can conclude alpha is equal to 36 degrees, given of course to the nearest degree. For part C of the question, the mining company plans to drill vertically downwards from the point 512.0 on the ground to reach the mineral layer. Using the model, we have to determine in meters to one decimal place the distance the mining company will need to drill in order to reach the mining layer. Well, for part C, I've drawn a diagram to illustrate what's going on. We've got the plane pi1 in Cartesian form, that's 13x minus y plus 18z equals minus 1035, and we've got the plane pi2, that's z equals 0. We've got the acute angle between the planes, that's alpha, and we've got this point 512.0, which lies on this plane here. Of course, z is equal to 0. Now, we need to find the distance by drilling vertically down from this point. This distance we're going to call lambda. Now, the x and y coordinates will be the same, however the z coordinate will be different. So here we've got the point 5, 12, and we've got some point z1, we'll call it. This point lies on this plane here, and the distance between this point and this point is going to be lambda. So if we substitute in the point 5, 12 and z1, we've got minus 13 lots of x, which is 5, minus y, so that's minus 12, plus 18 lots of z1. This is equal to minus 1035. And what we can do with this is find out what z1 is. z1 is therefore equal to, well, let's just simplify as much as we can before we work anything else out. We've got minus 13 times 5 minus 12, so that's minus 77. So we've got minus 77 plus 18 z1 equals minus 1035. So we've got minus 1035 plus 77. You can then see 18z1 is equal to minus 958. So z1 is equal to this divided by 18, which is minus 53.2, etc. And so therefore, we've got 5, 12, and minus 53.2, etc. So therefore the distance lambda is the distance between 0 and this, which is equal to 0 minus 53.2, etc., which is 53.2, etc. So therefore the distance lambda is equal to 53.2 meters, given to 1 decimal place. Now, for part D, we have to state a limitation of the assumption that the mineral layer can be modelled as a plane. So, a limitation is the mineral layer will not be a perfectly flat or smooth, and so will not form a plane. Question number 7. f of z is equal to z to the 4 minus 6z cubed plus pz squared plus qz plus r. P, q and r are real constants. The roots of the equation f of z equals 0 are alpha, beta, gamma and delta, where alpha is 3 and beta is 2 plus I, and given that gamma is a complex root of f of z equals 0, we have to, for part A, write down the root of gamma for the first part. Well, because we know that the roots come in conjugate pairs for polynomials with real coefficients, the conjugate of 2 plus I is 2 minus I. So therefore, gamma is equal to 2 minus I. And now for the next part, we have to explain why delta must be real. Well, we know already that the roots of polynomials with real coefficients occur in conjugate pairs. We also know that beta and gamma form a conjugate pair. Now, as we know that alpha is real, in other words, we can think of it as number plus imaginary, it would follow then that delta must be real. Now, for part B, we have to determine the value of delta. Well, if we take a look here, we can use the sum of the roots. So, for part B, the sum of the roots, that's equal to alpha plus beta plus gamma plus delta. That's going to equal minus 6. Of course, this minus 6 comes from here. So the sum of the roots is equal to 6. Now we know what alpha, beta and gamma are. So we have 3 plus 2 plus I plus 2 minus I plus delta equals 6. 7 plus delta equals 6, from which we can conclude that delta is equal to minus 1. Now for part C, hence determine the values of P, Q and R. So here is our polynomial, which I'll just rewrite over here. We have f of z equals z to the 4 minus 6z cubed plus pz squared plus qz plus r. Now, what we can do is find the values of p, q and r by working backwards from f of z equals 0. So if I set this equal to 0, and knowing what the roots are, alpha, beta, gamma and delta, we can say then that we have z minus alpha, z minus beta, z minus gamma, z minus delta equals 0. Of course, then we'll end up with the roots, which we already know. Now, what else do we know so far? Well, so far we know alpha is equal to 3. We also know beta is equal to 2 plus I. We know gamma is equal to 2 minus I, the complex conjugate of this. And we also know that delta is equal to minus 1. And if we substitute these back into here, we've got z minus alpha, so we've got z minus 3 being, well, let's just be clear on this. We've got z minus alpha, z minus beta, z minus gamma, and z minus delta equaling 0. So we've got z minus 3 multiplied by z minus 2 plus I multiplied by z minus 2 minus I multiplied by z minus minus 1. And all of this is equal to 0. And so, if we were to tidy this up even further, well, here we have z minus 3, and here we've got z plus 1. And then for z minus, then in brackets 2 plus I, and then z minus, and then in brackets 2 minus I, we can rewrite that as follows. We can rewrite that as z minus 2 minus I multiplied by z minus 2 plus I. And at this point, hopefully you can recognize we have a difference of 2 squares here and here. Now, z minus 3 lots of z plus 1. We've got z squared, and then here we've got z times by 1, which is z. And then we've got minus 3 times by z, which is minus 3z. So we end up with minus 2z there. And then minus 3 times by 1, that's minus 3. And then here we've got z minus 2 times z minus 2. Well, that will be z squared minus 4z plus 4. So all I've done here is multiply this by this to get me this. And then I've got minus and a plus, which is minus, and I times by I, that's I squared, which is minus 1. So I've got z squared minus 2z minus 3 lots of z squared minus 4z. 4 plus 1 is 5. And all of this, of course, is equal to 0. So now if I expand out and simplify, z squared times z squared, that's z to the 4. Z squared times by minus 4z, that's minus 4z cubed. Z squared times by 5, that's 5z squared. Minus 2z times by z squared, that's minus 2z cubed. Minus 2z times by minus 4z, that's 8z squared. Minus 2z times by 5, that's minus 10z. Then we've got minus 3 times by z squared. Minus 3 times by minus 4z. And then we've got minus 3 times by 5. And all of this is equal to 0. And if we collect everything together, we have z to the 4 minus 6z cubed plus 10z squared plus 2z minus 15 equals 0. Compare that with this polynomial over here, so let's just copy and paste this over here. We can therefore conclude P is 10, Q is 2, and R is minus 15. Now for part D, we have to write down the roots of the equation f of minus 2z equals 0. Well, the roots of f of z, we've got z equals 3 minus 1, 2 plus I, 2 minus I. So the roots of f of minus 2z, what we'd have to do is apply a transformation to each of these roots. We multiply each of these roots by minus 1/2. So we would have z equals minus 3 over 2, 1/2, and then here we have minus 1 plus minus 1/2 I. So these are the roots of f of minus 2z equals 0. Question number 8. For part A, we have to prove by induction that for all positive integers n, the sum from r equals 1 to r equals n of r lots of r plus 1 lots of 2r plus 1 is equal to 1/2 n lots of n plus 1 all squared lots of n plus 2. For part A, we begin by testing out what happens when n equals 1. For the left hand side, we've got the sum from r equals 1 to r equals n of 1 lots of, well, the sum from 1 to 1, that will equal the sum from r equals 1 to 1 of r lots of r plus 1 lots of 2r plus 1. So we get 1 lots of 1 plus 1 lots of 2 lots of 1 plus 1, which is 6. And on the right hand side, if we replace n with 1, we've got 1 lots of a half times by 1 times by 1 plus 1 squared multiplied by 1 plus 2, 3 times by 4 times by a half is 6. And because the left hand side and the right hand side are both equal to 6, we can therefore conclude that the result is true for n equals 1. Our next step is to assume that the result is true for n equals k. And if we do that, we are assuming that the sum from r equals 1 to r equals k of r lots of r plus 1 lots of 2r plus 1 is equal to 1/2 k lots of k plus 1 squared lots of k plus 2. We're just substituting n for k. And now we will see what happens when n is equal to k plus 1. So what we are doing, we've got the sum from r equals 1 to r equals k plus 1 of r lots of r plus 1 lots of 2r plus 1. Well, this is equal to the sum from r equals 1 to r equals k of r lots of r plus 1 lots of 2r plus 1. And then we add on to this the k plus 1th term, which means we replace the r with k plus 1. So we add on k plus 1, lots of k plus 1 plus 1, multiplied by 2 lots of k plus 1 plus 1. Now, if we use our assumption with what we found here, we have 1/2 k, lots of k plus 1 squared, lots of k plus 2, so that's the assumption of the result for r equals 1 to r equals k, so that's here. And then we add on to this k plus 1, k plus 1 plus 1, lots of 2 lots of k plus 1 plus 1. So let's tidy all of this up. We've got 1/2 k, lots of k plus 1 squared, lots of k plus 2, plus k plus 1, lots of k plus 2, and here we get 2k plus 3. So now we need to tidy all of this up. And if we go back to the question, let's think about what our goal is. If we think about what we want to show, we want to replace the n with a k plus 1. We want to show we end up with a half lots of k plus 1, lots of k plus 1 plus 1 squared, lots of k plus 2. That's what we want to show. Now, k plus 1 plus another one, that's k plus 1 all squared. Now, both terms, if we go back here, contain a k plus 1. They also contain a k plus 2. So, if we take out the half, and then a k plus 1, and then a k plus 2, inside this big bracket then, well, we'd have k, lots of k plus 1, so this multiplied by this gives this, and then we add on 2 lots of 2k plus 3. As we see here. So we've got 1/2 k plus 1, lots of k plus 2, and then we've got k times by k, which is k squared. We then add on k, we then add on 4k plus 6. So, tidying this up even further, we've got a half lots of k plus 1, lots of k plus 2, lots of k squared, plus 5k plus 6. And we can factorize this. So we've got 1/2 k plus 1, lots of k plus 2, lots of k plus 2, lots of k plus 3, which is k squared plus 5k plus 6 factorized. And you'd find we get k plus 2 being multiplied by itself, so we've got 1/2 k plus 1, k plus 2 squared, lots of k plus 3, and if we pay attention to what we want to show, you'd find we got k plus 1, lots of k plus 1 plus 1 all squared, lots of k plus 2. So what's happened here is, we end up with 1/2 lots of k plus 1, lots of k plus 1 plus 1 squared, lots of k plus 1 plus 2, and of course this result is exactly what we wanted to show over here. So now we need to move on to our conclusion step. So if the statement is true for n equals k, then it's been shown true for n equals k plus 1. And as it's true for n equals 1, it's true for all positive integers of n. Now for part B, hence show that for all positive integers n, the sum from r equals n to r equals 2n of r lots of r plus 1 lots of 2r plus 1 is equal to 1/2 n lots of n plus 1 lots of an plus b lots of cn plus d. So for part B, well, let's begin by defining f of r to equal r lots of r plus 1 lots of 2r plus 1. Hence, the sum from r equals 1, rather, the result from r equals n to 2n of f of r is equal to the sum from r equals 1 to r equals 2n, because remember, we want to start off at r equals 1, and then we need to take away the sum from r equals 1 to r equals n minus 1 of f of r. So what we will do here is we will replace the n from here with 2n and n minus 1 respectively. Let's just change the colours. Here we've got a 2n, and here we've got the n minus 1. So if we work this out, we've got 1/2 lots of 2n. If we replace as necessary over here, and then we've got n plus 1 all squared. So instead of us having an n, we have a 2n, and then we have a plus 1 all squared, and then we've got an n plus 2, which is being replaced by 2n plus 2. And then we subtract 1/2 lots of, well, instead of us having an n, we've got an n minus 1. So we've got n minus 1, and then we've got, well, let's just write this down. Here we've got an n minus 1 plus 1 squared lots of n minus 1 plus 2. So let's tidy all of this up. We have 1/2 lots of 2n lots of 2n plus 1 squared lots of 2n plus 2 minus 1/2 lots of n minus 1 lots of n squared lots of n plus 1. So we need to tidy this up even further. Well, 1/2 times by 2n plus 1, rather 1/2 times by 2n plus 2, that's just going to be n plus 1. So we've got 1/2 times 2n times 2n plus 1 lots of n plus 1. So that is the result of multiplying this with this to get this. And then we take away 1/2 n minus 1 times by n squared lots of n plus 1. And if I take out a 1/2 n lots of n plus 1 as a common factor, what we end up with in this bracket is a 4n, rather a 4 lots of 2n plus 1, and rather this is squared, minus n lots of n minus 1. So, continuing to tidy this up, we've got half n lots of n plus 1, and then we've got 4 lots of 4n squared plus 4n plus 1 minus n squared plus n. So we've got 1/2 n lots of n plus 1 lots of 16n squared plus 16n plus 4 minus n squared plus n. So we've got 1/2 n lots of n plus 1 lots of 16n squared, rather 15n squared plus 17n plus 4, and then factorising this, we can conclude we have 1/2 n lots of n plus 1 lots of 3n plus 1 lots of 5n plus 4. This is our final answer. Question number 9. Figure 2 shows the vertical cross-section AOB CDE through centre A of a wax candle. In a model, the candle is formed by rotating the region bounded by the y-axis, the line OB, the curve BC and the curve CD through 360 degrees about the y-axis. Point B has coordinate 3, 0, so let's just add this on. We've got the point B with coordinate 3, 0, the point C with coordinate 5, 15, and the units are in centimetres. The curve BC is represented by this equation here, square root of y equals square root of 225x squared minus 2025 over a, where x is in between 3 and 5 and a is a constant, and we have to determine the value of a according to this model. So here we've got the curve y equals 225x squared minus 2025 square rooted over a. Now what we can do, we know C lies on the curve, so if we use that point of 5, 15, we can find out the value of a. So for part A, if we use the point 5, 15, we have 15 equals 225 lots of 5 squared minus 2025. This is square rooted, and then we divide by a. So we have 15 equals something over a. So it's square root of 225 times 5 squared minus 2025, that's 60. So of course a is equal to 4. So this equation here is y equals square root of 225x squared minus 2025 over 4. So let's just write that down here. We have y, which is equal to square root of 225x squared minus 2025 over 4. Now for part B, the curve CD is represented by the equation y equals 16 minus 0.04 x squared, where x is in between 0 and 5. So let's just write this down. We've got y equals 16 minus 0.04 x squared. Well, that's just 1 over 25. Then we've got the x squared. And we have to use algebraic integration to determine, according to the model, the exact volume of wax that would be required to make the candle. Well, to find out the volume, because we're rotating 360 degrees about the y-axis, the volume of revolution, that's given by pi lots of the integral between two limits of x squared with respect to y. Now, if we think about the curve BC, which is this equation here, we can rearrange for x squared. So, multiplying through by 4 to begin with, we have 4y equals 225x squared minus 2025 square rooted, and then squaring both sides. We've got 16y squared equals 225x squared minus 2025. So therefore, x squared is equal to 16y squared plus 2025 divided by 225. And if we think about the curve DC, well rather CD, we know this has equation y equals 16 minus 1 over 25 multiplied by x squared. And so if we rearrange, x squared is 25 lots of 16 minus y. So we have x squared given, and now we can find out the respective volumes. What do I mean by that? Well, if I split this up into two parts, like so, we can find here V1, and we can also find V2, and then we can find out the total volume. So, if we were to find out what V1 is, V1, so V1, remember V1, we're going to be rotating CD about the y-axis. The limits over here, well, before we do anything else, what's the coordinate of D? Well, when x is 0, y is 16. So here we've got 0, 16. So for the limits of y, we're going from 15 to 16. So V1, that's given by pi lots of the integral from 15 to 16 of 25 lots of 16 minus y dy. So I've got 25 pi lots of the integral from 15 to 16 of 16 minus y dy. In other words, I've got 25 pi lots of 16y minus 1/2 y squared between 15 and 16. And if I work this out, we've got 25 pi lots of, well, for the upper limit, we've got 16 lots of 16 minus 1/2 lots of 16 squared minus 16 lots of 15 for the lower limit minus 1/2 lots of 15 squared. So what do we end up with over here? Well, 16 times 16 minus 16 squared times 0.5 is 128. And then we've got that minus 16 times 15 minus 1/2 times by 15 squared. And then I'm going to multiply that by 25 pi. So it turns out we get 25 pi over 2 centimeters cubed for the volume of V1. And we can find out the volume of V2. We're going from 0 to 15, and we will be integrating the result we found here. So the volume of V2 we can find again using integration. We have pi lots of the integral from 0 to 15 of 16y squared plus 2025 divided by 225. We integrate between 0 and 15 with respect to y, of course. So we have pi over 225 lots of the integral from 0 to 15. Well, we can write this out smaller. So here we've got pi over 225 from the integral from 0 to 15 of 16y squared plus 2025 dy. So we've got pi over 225, and then we've got 16 over 3 y cubed plus 2025y evaluated between 0 and 15. And if I substitute in 15 for my upper limit, for my lower limit, I've just got 0. We've got pi over 225 multiplied by 16 over 3 lots of 15 cubed plus 2025 lots of 15. And for the lower limit, we've just got 0. So if we work this out, what do we have? 15 cubed times 16 over 3 plus 2025 times 15. And then if I divide this value by 225, I get 215 pi centimeters cubed. So what can we say from this? the total volume that's equal to V1, 25 pi over 2, and then we add on to this 215 pi. So if I do 25 over 2 plus 215, we get 4, 5 pi over 2 centimeters cubed. So this is the total volume, and if we find out the decimal equivalent of this, we've got 714.7 etc. centimeters cubed. So that's the total volume. And now for part C, we have to state a limitation of the model. Of course, here the sides of the candle will not be perfectly smooth. Now for part D, when the candle was manufactured, 700 centimeters cubed of wax were required. Using this information in your answer to part B to evaluate the model, explaining your reasoning. So from part B, we saw that the volume was approximately 715 centimeters cubed. Well, here's the exact volume. So we have a good estimate, and that's because 700 centimeters cubed is only 15 centimeters cubed less than 715. The values are really close to each other. So the model is quite suitable.